Okay, so today I want to drive you through the example of an exam that you could have about convex optimization. So, for example, I think what the first question could be just like what is semi-definite programming, and so you can say like semi-definite programming could be like just it just like linear constraints and semi-definite constraints. Um, Semi-definite constraints because at the end, like if we remember about the course, we saw first that we had like there's a sentence that says that um, linear is not sufficient. Like if you want to do optimization about something, then it can be like not sufficient to have only linear, like thing like optimization is like not between linearity and non-linearity, but it is between convexity and non-convexity. It's like Rockefeller who said it. So the great Waters in optimization. The big move in a way is not between linearity and not linearity in optimization, but really in convexity and non-convexity. And so linear programming can like simulate like linear stuff with linear constraints. But so if you want to do convexity, because you will not semi-definite programming like linear constraint, but also semi-definite passive constraints can handle it, because like convex optimization is like everywhere in machine learning, control theory, and economics, computer vision, network, and many more. So yeah. Um, Yeah, we. That's why I think because this course focused on so many different programming, I think you can just say it's this, and so after you can explain it with the real stuff, like how to say about it. Like you can like say, well, we know like convex optimization can be written like this. Um, but like so linear programming is like the most simplest family of problems of convex optimization, like which are linear programming, which are this one. So above C transpose of x such as that ax is inferior to b and x is superior to 0. And so yeah, so you have your objective function here, but you see here you have only linear constraints, and so yeah. If you see one of my video, I want to throw an example of linear programming with some chairs and tables, so you can understand really. But so the main stuff is like semi-definite programming is like literally the same as linear programming. So it's an objective function with linear constraints, which represent like less from or this. But you have something else. You have also semi-positive definite constraint. So yeah, I think if you say this, like just saying that SDP, like it just linear constraint plus semi-definite constraint is alright. Yeah, and that's really cool about them because like convex optimization problems in LP and SDP, they're somewhere you can guarantee global optima efficiently. So that's really optimization paradise because like you can know about it. But yeah, so the question was like, what is SDP? It's just linear constraint, semi-definite positive constraint. So that could be the first question. The second question you could go about could be like Um, can you like give some applications of the of semi-definite programming? And so you can answer about that too. So by the way, here you should say also like, well, you can write this, and so it's no matter I. Like if you want to really like want to consider it like a general SDP, like can unseparate the constraints. Like you can say this, like this being inferred to AI, and having also a trace of GGX being equal to BG no matter G. And so after when you derive the Lagrangian, you'll see that like the lambda G here will be superior to 0 or inferior to 0, depending on like here superior to 0, and if the sign is like here inferior to 0, to respect the indicator function, and here just into R because it's inequality, so you just have like x equal y minus x equal minus y, so you don't care about the sign of the lambda when you derive the Lagrangian. But yeah, so yeah, you have this, and so yeah, you can say like what's the applications of it, and so there is a lot of applications. There is like so that was the first question, what is the first question could be like, what is SDP? Just a way to optimize where you have linear constraints and semi-definite positive constraints, so linear programming semi-definite positive constraints. So the second question could be just like formalize it, in a way. Yeah, just write the definition. The third question could be like, can you give applications of it? So as I explained in different videos, you can have state discriminations. So you have different states, and so when you do quantum Shannon theory, you can discriminate between two states. But when you do SDP, you can discriminate between n states. So yeah, with the normal quantum Shannon in quantum Shannon theory, like you can have the Olivo-Elstrom theorem that can help you discriminate between two states, but it cannot discriminate between n states. So probability of one. So that's the Olivo-Elstrom stuff you can know about. And yeah, so that's in quantum Shannon theory, but in convex optimization, you can generalize it, and yeah, that's it. So yeah, that's it. So yeah, state discrimination, like with SDP, you can formulate it and discriminate between more than just two states in general. And so yeah, there is also entanglement witness, optimal cloners, contemporary operation, and so one question could be take the one you want between state discrimination, entanglement witness, or all the rest, where SDP can apply, and just give me its SDP and explain how it works. So let's suppose you choose state discrimination. You can say, well, then state discrimination, it's like just Alice assigned a state's row x to Bob with the probability px, and so in order to guess x, Bob should measure a POV on the states she is from Alice, and if the outcome is like y, then he gets that Alice send py, and yeah, so by maximizing, so yeah, if he maximizes about all the probability, he obtains the optimal guessing probability. So yeah, and so basically you can write it as an SDP, like literally like this, like the probability of success. It's just like, as I said, he must sum about probability, and so after he should take POVM and get the correct one, so he has a trace of rho x mx, and maximizing over this maximizing over the states of maximizing over the POVM on the states release he receives from Alice. As such, respecting the condition of a POVM, which is just the ones. So yeah, that's how we can write it. And so you can say here is thanks to SDP, you can now have an efficient algorithm that can identify the optimal measurement for discrimination, no matter the discrimination task. Yeah, so that's it. So maybe also before you say this, like you can say in the question 3 that you have state discrimination and convent witness, etc. But all of them represent at the beginning like uh, an application of quantum theory, like because here it's like it's just based on the property of states, is because the states are just have convex measurements same, like you have this property, like the sum of the measurements should be equal to the identity. MG should be like semi-positive definites, like it should be state trace a trace of rho should be equal to 1 or should be superior to 0. So semi-positive definites and yeah, and so and for the and for example for optimal cloners or counter error creations, it's based on channel. Also, you have channel being semi-positive definites, completely positive trace preserving, as a definition saying, and they have those properties. Where we use the fact that channel can be defined with the Chern matrix. So yeah, the just application of this arising naturally problem important to quantum information, such as state discrimination, antiqual witness, optimal clonus, quantum error correction. So that's about it. And so yeah, so you just described what was state discrimination, and so maybe we can say now like can we check about your understanding of SDP, and so um, yeah, we could also have developed an antiqual witness and yeah, antiqual witness and SDP, but with PPT you do a relaxation, but you can do over two by C3, like, or but qubit it works, but Q-treat C3 by C3, like complex 3 by complex 3, like complex 3 by complex 3, like this, it will not work, and so you will need to relax, and so PPT, and after relaxing with DPS, the hierarchy created by three person. This 3 letters are the abbreviation of the name of the person, and so yeah, but yeah, you can have an SDP about it at first, and yeah, so that's it. So now I do not know if I can help you with this, but yeah, I think it's alright. Um, so suppose now, like, we give you this question, we allow you finish your explication, and so I want to give you this question. Um, I just write it correctly. And so I see you like I give you a valid POVM, MX, a valid POVM, NX. Um, does there exist a state row that respects it, and especially the POVM themselves are fixed, um, because like trace of M or such that like trace M0P is superior to 1 minus epsilon, and the same for the second norm. And you'll see here like here the sign is not like the same as in the standard form. You just need to make attention about it. But yeah. So yeah, have this. And so the problem will be like, can you write a primal about it? Like, because like the goal of the course, for us, for me, and for it will be that you are able to formulate any very complex optimization problem within quantum theory. So you're gonna do it. Um, so yeah, um, you have this, and just try to formulate the problem. So basically, like uh, you want to maximize like a number, so because it returns you a number. So row is a matrix. You can take trace of row, for example. Such that you have already researched that here. Um, so yeah. The question is like, could you do it? There exists a state row, such that etc. etc. But like, you should understand like you just need to have the primal under the dual with the Lagrangians. So you can say, okay, then to do this, I will need to formulate my program first. So as I said, take tracer row because we need to return a number under the matrix. Because that's density matrix, because contimes takes a density matrix, the trace of row is equal to 1, by the way, so you should write it. Because the contimes takes density matrix, you should have a row being semi-positive definites. So normally, once you have ruled that, you have you have you have the answer to the question. And so after what you should do, like normally, like try to derive the dual things to it. Um, yeah. So as you see, you have this, and so after when you have done this, um, you just need to try to derive the Lagrangian to form the dual. So you can do it. You just take the Lagrangian. You don't need to go via the indicator function. You can directly go for the to in time. So you see the objective function, it's rho. So up you take it, max of rho. After here you see you have an inequality. So trace of rho is superior to 1 minus sigma. And so, yeah, you know that the standard form is like sub of x of the trace of cx, such that the trace of fi of x is inferior to ai, and so you need to take to be accurate with to be accurate with the stuff with the sign. And here we take superior to 0 to be accurate to the indicator function. So because in the other sense it's inequality, and to preserve the sign you should take a minus lambda, so lambda should be inferior to 0. So here it should be like lambda 1 inferior to 0, lambda 2 inferior to 0, because the sign are not a good thing. Here we don't care because lambda 3 can be into R because it's inequality, and here it's like a matrix, so you just need a positive semi-indefinite constraint because the other ones are just like not matrices, so it just some lambdas. Okay, so we have rho, lambda 1, lambda 2, lambda 3, and for the last one you can like call it y for the matrix you multiply by. Yeah, with lambda 1, lambda 2 being inferior to 0, lambda 3 being into R. So Lagrangian, just like trace of rho plus lambda 1 of 1 minus lambda minus trace of m0p plus lambda 2 multiplied by 1 minus lambda minus trace n0p plus lambda 3, because it's still numbers, like it's 1 minus epsilon or whatever, sigma, don't know the name of this stuff, but you got me. Plus 1 minus lambda 1 minus trace of p plus a trace of py, like rho y. Prefer. So you have this. And so after you just put uh, the raw stuff, what is not depending on row outside, so lambda 1 multiplied by 1 minus epsilon plus lambda 2 multiplied by I minus 1. It's maybe sigma, I don't know. But you got me plus lambda 3 plus um, trace of rho multiplied, like to be accurate, to be more funny, trace of rho multiply identity, because it's a matrix, so you multiply matrix by a matrix, plus even if the trace is before, we do not care, because rho is a matrix. So rho by identity, and after you take the trace, like you do the operation in this order. So yeah. Rho identity minus lambda 1 m0, then like tracer from minus lambda 1 trace of m0 rho minus lambda 2 n0 plus minus lambda 3 plus y. And so based on this, you can write that we have the inf, or the mean, because we take the max, of lambda 1, lambda 2, as we write first, inferior to 0, and lambda 3 being into R. Okay. Have the mean of lambda 1, lambda 2 inferior to 0, and lambda 3 being into R. Such that we have I equal lambda 1 and 0 plus lambda 2 and 0 plus lambda 3 minus y, because you just take this equal to 0, and so you just pass this to the other part, and so because you pass this to the other part, you just take I, and so I is equal to this. Yeah. So normally you derive the Lagrangian, you find this, and can try to go to. Well, in a way, yeah. So yeah, in a way we can say like deriving the Lagrangian was the sixth question. Seventh question like is to write the dual. Eighth question could be like because it's not conventional, like the stuff about the lambda, it's just easiest to simplify the form, like just to say, can you explain why like lambda try minus one trace of p like is he into R like or not, and yeah, just explain what the sign of, and we want to minimize about rho, and say yeah, you want to minimize, so you just take one minus trace of p, and you're like, okay, like how can I, okay, trace of p is normally like if trace of p is equal to 1, like it will be equal to like just the maximum of trace of p is like 1. So trace of rho. So yeah, suppose it's inferior to 0, which normally will not even happen, but because like trace of rho should, but yeah, but suppose, then it means like if it's inferior to 0, you just want lambda 3 to go into infinity, because you want to minimize. But if it is superior to 0, which normally is the case, then you want from the 3 to go minus infinity. And yeah, no, so if it's a super inferior to 0 like this, then it just means we want lambda 3 to go to plus infinity, so we have a minus infinity. So in the other case, where it is superior to 0, so it's a true condition, we want this to be true, so we want 0, and so lambda 3 should go to 0. So yeah, just to you explain in a way why we chose like lambda 3 like could be in our case like superior to 0. The eighth question. So now for the ninth question, we can like ask you like now that we in a way like the goal of the course was tracing, it was to formulate an interconnex optimization plan using quantum theory. So we take state discrimination and we went over it and we tried to take an example with some fixed proven and we write a primal about it, and after we made the second goal, we derived the ultimate indefinite program and used duality theory to help solve the problem. And so the third goal will be like just to understand apply semi-definite programming relaxation where it keeps operating within quantum theories. Maybe the first question, like as we ask what was SDP, we could ask like what is like polynomial optimization. You can say like yeah, it just you have some polynomials, and so it's hard to find directive values about those polynomials, and so what's the optimal minima, for example, etc. By the way, the better properties like all local minima, global minima, that's connect stuff. But so yeah, you can say this, and so you can say relaxation can when it's hard, you just take a bigger set of the little set of the polynomial, and so just you check about the monomers, like first like it's a level 1 x, like if you have two variable x and y, and after like level 2 like 1x and y, and after level 2 and we multiply them in the matrix, after level 2 1x y x1 x y xy y squared x squared, and then multiply them in the matrix there on. And so yeah, you can say polynomization just like find on a polynomial, like just like the definition could be like a sub of fx1 to fxn, where f is a polynomial such that gi of x1 to xn is superior after I leading into 1m, ag x1 xn equals 0, letter g leading into 1 to r, and yeah, where like we have f, gi, and ag polynomials, and xi leading into r. So yeah, you have your polynomial f, and you have like constraints on your on other polynomials, and so you can find like different applications such as the mask gets problem that can be represented into it, and so you can say like how can you solve it. And so there is two approaches. The dual approach, the moment approach, and the sum of square approach. And so we can do like take like your favorite one. Like so, suppose you say like moment approach because like it takes less time to compute, etc. If you're better with it, so you take moment approach. And so we would just say, okay, bros, and you're gonna apply your knowledge about it, like the definition, and try to do an exercise and take a polynomial and derive the moment approach, and say it about her. So yeah, you can just like take like your own polynomial, or try to derive to prove it, or like taking this one or another one, and just like, yeah, you could have something like this, for example, on they take like go person moment approach level 1. So you just take the moment matrix at level 1. So basically, I explained in the video, but like you have 1xy, 1xy, but because you want to trick the computer, you directly take like 1y01, y02, y11, y22, sorry, and so with the index, so here y01, y02, and so here y12, and so here it's symmetric, because these are Hermitian matrices. It's one of the four properties of moment matrix. And so you just have this, and you can write like we can write about it like to say, okay, well, you have this, and so to return scripture problem, you just have the inf of xy of x squared, which would be like y11 plus y squared y22 minus 2y12 for xy, such that you have, until let's suppose we impose a condition like x squared is equal to x, and so you just have to write like 1, y01, y02, but this is the same here, but because x squared is the same as x, you can write it as x, so that's x, y01, and here's like y12, and here's like y22, and so being semi-positive definite. So yeah. And so yeah, the question that you can have after you've done this is just like, okay, that's cool, but now suppose you do like you did a level relaxation of level 1. If you did a level relaxation of level 2, what would have happened? Like, would you have like a bigger value, or a value even less bigger? And so you can say, well, okay, so we have our set S at the beginning. We did after level relaxation um, of level like of level 1, and after one of level 2. And so the fact is, the more you go inside, the less the set is bigger. So the more you relax the sets, the more you have the ability. And so suppose like the inf should be like 0, then suppose you find 0, then here you'll have 0 and maybe other stuff like -8, and here you have at least 0, -8, and maybe -15. So it means like you would have, at least with the new relaxation, a value that would be inferior to what you find in the initial set. So yeah, by relaxation of level by a relaxation of level so there's two questions here. So when you relax even level 1, then you'll see like an inferior value, or not strictly inferior, like it can be 0 2, but it can on R2, like it will be like a less restrictive set, so compared to R1 it will reduce, so you can have like you got me, like in the initial set you have 0, so in R1 it means um, in R1 it means you have like you can have it will be inferior or equal to 0, and in R2 is like uh, it's like between R1 and S. So yeah, like it's like the intersection S and R1 in a way. Well, there is, you can have the relaxation extra. But yeah, in a way, so if you go like simplify the question, we just say like R1, then it will be an inferior value. And so yeah, if we can write it like this, like R2 also like will be like inferior to 0, and R1 like will be inferior to 0. Um, yeah, I can like even say like this: S1 inferior to 0, and R1 inferior to R2. So yeah, that will be the correct way to represent it. So you demonstrate that you understand that it will be inferior to what you have the set. What will you return this? So numerical value that will be returned. You know that it will be like inferior to it. So because like yeah, you find numerically the solution of this problem, and you know it will be inferior. And so the epsilon value, yeah. Yeah. So I think you got the idea. So now that you demonstrated that, you can formulate an interface configuration optimization problem, you can derive some different programs and use duality to solve the problem, and you understand the placement hierarchies to the problem within contemporary. Well, we didn't do it within contemporary here, it was marginal, but like you can like ask an intuition question, which is like, how can we like with the moment, like if we wanted to do the level relaxation of level n, how would you do it? And so what you can say, could just iterate, think of what you do at level 1, level 2, level 3, and you'll see the pattern coming for level n. So at level 1, like have 1, x, y, have like um, this, and this. At level 2, so that's level 1. At level 2, you have 1, x, y. In our case, because it was x equal x squared, have like xy y squared, and then about e squared. And same here, xy y squared. And so at level 3 you can have the same, like 1 xy it's y squared, xy x squared y, so it's still xy, but after you can have xy cube. You can have also like y cube, and y by itself is like y to the power of 4. Um, and yeah, so you can have like this one of this y3, and multiplying now here and here. And so you just need to multiply now, like you have the stuff, 1x squared, y squared. It's like, yeah, so after you have like xy, so after you have like y to the power of 4, and yeah, that's it. Like, here we had a 1, x squared, so it's x, y squared, it's xy, and here like we have 1, x squared, um, y squared, so x squared y, so xy, y xy, so it's xy squared, uh, and after we have like xy to the power of 3, like y squared 4, and so same here, and after, so you have like, and at the end for level n, it seems like you just multiply here again, so you have white 8, so just seem like to be y to the power of 2n, and with all its mono, well, with all its mono, with with all its monomials. And so you have y to the power 2n on all of its monomials. So you know this and all the combination, so the monomials, yeah. So yeah, that's it, and you proved your intuition, and that's your end. That's the end of it. I think that could be a type of little exam, for example.